So let's talk about um, the idea of half-life and doubling time now. So first of all, what this means is the amount of time it takes an exponentially growing quantity to double is called the doubling time. The amount of time it takes an exponentially decaying quantity to decay by half is called the half-life. So let's look at these formulas here. So something that's growing can have a doubling time. And with this example, we saw that the amount of algae is doubling every week. And that's happening because you sort of have this sort of growth factor kind of thing of 2 here, but it doesn't go up by a factor of 2 every day. It goes up by a factor of 2 every time the exponent goes up by 1. The exponent goes up by 1 every time d goes up by 7. And when the exponent increases by 1, the amount of algae goes up by a factor of 2. So the doubling time here is 7 days. So for exercise 2, this is something that's decaying. So how long does it take for it to get reduced by half? It took 500 years. So the idea is here that y over 500, the exponent of 1/2, increases by 1 whenever y increases by 500. So that is the half-life of this. Now, these exercises were supposed to sort of lead you to why this formula makes sense. The first thing to notice is that in math, as well as in programming code, uppercase letters and lowercase letters stand for different things. So here, little t is the variable here, and big T, uppercase T, is a constant. It's going to be a number. So in this case, if a quantity has initial value A, the initial value is the same as before, and grows by a growth factor of B every big T units of time, then this is the formula for it. So whenever little t, the variable, is equal to big T, that's going to make the exponent 1. Every time little t increases by big T, the exponent will increase by 1. The whole thing gets multiplied by another factor of b, and that's why it has a growth factor of b every big T units of time. So, so little t is the variable, big T is the constant. Let's try to apply this rule to this situation with these bacteria. So we have bacteria A increases by 30% every hour, and bacteria B doubles every 3 hours. Each starts with 500 bacteria, and we want to know which is growing faster. Let's find the doubling time of bacteria A by graphing it with a calculator. So there's a lot going on here with this example. If we want to know which one is growing faster, we can't really compare these right now. Bacteria B doubles every 3 hours, so you might be thinking that, well, if bacteria A increases by 30% every hour, then in 3 hours, is it going to increase by 3 times 30% or 90%? If so, that's less than doubling, because doubling is the same thing as increasing by 100%. So if that's the way you're thinking about it, that's totally reasonable. But it's not exactly how it works. So increasing by 30% 3 times, we're going to see, is not actually the same thing as increasing by 90%, which is a weird thing about exponential functions. So to figure out what's actually happening, let's get a formula for each of these. So let's say that T is the number of hours, and we can get a formula for the amount of bacteria A after T hours. And it starts with 500 bacteria. They each start with 500. So that's the A. And it's increasing by 30% every hour. So we can write this as 1 plus 30% to the power T. So every time T goes up by 1, we're going to multiply the amount by another factor of 1.3, which increases it by 30%. So that's the formula. We could also write this in the form 500 times 1.3 to the power T. So that sounds good. Now that's A of T. How can we get B of T? Let's see. It's also starting at 500. But this one, it says, is doubling every 3 hours. So doubling every 3 hours means growing by a factor of 2. So the B in this formula is going to be 2. And the T is going to be 3 hours. So the formula here is going to be 500 times 2 to the power little t, the number of hours, divided by 3. So to check that this works, if you're going to, we could make a little table, I think, to help understand this. After 0 hours and 3 hours and 6 hours. So after 0 hours, you got 500. After 3 hours, this is going to be 500 times 2 to the power 3 divided by 3. 3 divided by 3 is 1. So this gives you 500 times 2 to the power 1, which is just 500 times 2. That makes it double to become 1,000. If you plug in 6, you're going to do 500 times 2 to the power 6 over 3. That's going to make it double again, because 6 over 3 is 2. So we get 500 times 2 to the power 2, which is 500 times 4, which gives you 2,000. So that made it double a second time. Okay, so that works. Now, which is growing faster? Well, we can't really tell yet. They're not written in the same form. If you want to know what the doubling time of what the percent growth rate is every hour, we would need to write this in the form like this, 1 plus something to the power t. So to do that, this is going to turn into 500 times 2 to the 1/3 to the power t. Here's your Appendix G rules coming in again, that you need to know how to do that. 2 to the power 1/3 is the same as, I need a calculator for that. 1.26 to the power t. So this is a growth factor of 1.26. If you want to know the growth rate, you need to write this as 500 times 1 plus r to the power t. So that r is going to be 0.26, because 1 plus 0.26 is 1.26. So the hourly growth rate is just 26%. And when you compare that with 30% that the other one's growing every hour, this is not growing as fast. So let's think about why that happens here. Like, why, if you just increase by 20% every hour, how does that lead you to doubling in 3 hours? Well, if you do 500 times 1.26, that's going to give you 630. If you do 630 times 1.26 again to see how this is growing, this is now going to be increasing by 26% of 630 instead of 26% of 500. So first it went up by 130. That was the 26% of 500. Now it's going to go up by 26% of a bigger number. And it's instead of increasing by 130, now it's increasing by 163.8. And then what if we do this again? 793.8 times 1.26, you'll get 1,000. And there it is, doubling in 3 hours by increasing by 26% each time. Now, if you increase by 30% 3 times, if you take 500 times 1.3, that's going to increase by 30%. Okay, it's going up by more, 650. If you then do 650 times 1.3 to make that increase by 30% more, it's going up by even more. And then 845 with another 1.3 factor. Now this is 30% of 845. So it's not 30% of the original 500. It's going up by 30% of more. You get 1,098.5 bacteria. So yeah, so which is growing faster? The one with the 30%. Now, how can we find the doubling time of bacteria A? We can see that it's going to be a little bit less than 3 hours, because after I increase this by 30% 3 times, we get 1,098. So we can graph this with a calculator. I'm going to graph y equals 500 times 1.3 to the power x. Hello. Okay, I'm back. I got interrupted for a second there. When we graph this, we want to make it so the window is kind of reasonably describing what we're talking about. So the x min and x max should be talking about like the range of hours that we're thinking about. So we know it's going to be something less than 3 hours. You could get a pretty good window if we say we're talking about from hour 0 to hour 5. So something kind of in that range. And the y min should be 0, because you can't have fewer than 0 bacteria. Or you could, I don't know, there's other things that might work. I'm just trying to get something reasonable. The y max, well, I want to see when it doubles, when it gets to 1,000 bacteria. So I'm going to make this be, I don't know, 1,500 or 2,000 or something like that. We should get a decent idea of the graph. So this is the graph of the amount of bacteria in the population A, bacteria type A. So we want to know, when does it double? Well, it doubles when it gets to 2 times 500. So I'm going to, before I actually do this, I just want to write out the equation we're trying to solve. So the doubling time is the solution of this equation here. 1,000 equals 500 times 1.3 to the power t. So if you want to solve this, we're going to graph y equals what we have, and we also need to graph y equals 1,000 to see where they intersect. So over here we're going to have y equals 1,000. We need to see what x shows you that intersection. So to get an intersection point, it's the same way we've done it before. Second calc 5 for intersect. Press enter for the first curve, enter for the second curve. There's your guess. It is 2.64 hours later. So yeah, a little bit less than 3 hours. So we can say the doubling time of A here is 2.64 hours. Okay, so yeah, that's a pretty rich example with a lot going on. So if you didn't understand everything in there, it's probably okay. This is a good example where you might need to go back and review some of the stuff I said. Maybe you need to work out some of the arithmetic yourself if you're not following what I'm doing. But let's look at example 2 next whenever you're ready. So we want to write a formula in this form and an equivalent formula in this form to find the growth rate. Remember, the growth rate here is always going to be whatever R is. So for A, we have that the value of a stock begins with $5,000 and triples in 21 years. So the initial value, that's always going to be the A, that's 5,000. And it triples in 21 years. That tripling is describing a growth factor of 3, but it's not a yearly growth factor. It's a 21-year growth factor. So this 21 years is the T in the formula from up here. It's a growth factor of 3 every 21 years. So this is going to be 3 to the power little t over 21. So we've got it in that form, but now what if we want to know the yearly growth rate? Like, what percentage is the stock actually going up? Well, we're going to have to do some little exponent tricks here. This is going to become 3 to the power 1 over 21 to the power t. Because 1 over 21 times t is the same thing as t over 21. Now, we can get that 3 to the 1/21th with a calculator. It is about 1.0537. So what is the growth rate? The growth rate, it needs to be written in this form. So right now we have it with the 1 point that, but instead of 1.0537, we want to write this as 1 plus something. And that something is the growth rate. So how about 1 plus 0.0537? That's 1.0537. So yeah, that's the growth rate. Is, you could write it as 0.0537, or maybe you want to think of it as 5.37%, which is the way it would show up in a real life description of this number. All right. Now we have the price of a certain cell phone started at $600, but fell to $500 after 8 months. Okay, so we know it's going to be Q equals 600 times B. I don't know what the B is yet. We're going to have to figure that out. But it's going to be, B is whatever you multiply by to make it go from 600 to 500 every 8 months. And it's saying every 8 months, so this is going to be T over 8. Now, how can we figure out what that b is? Well, let's see. B is what you multiply by 600 to make it go down to 500. This is a tricky example. If this was to show up on a test, it would probably be extra credit. So yeah, what is this 8 monthly growth factor here? To get that, what do you multiply 600 by to get 500? That would be, you just divide both sides by 600 here, and you'll get 5 divided by 6. Okay, so that's the b. So you can write this formula like so. Q equals 600 times 5/6 to the power t divided by 8. Okay, so now what is the monthly decay factor here? So we're going to do the same trick as we did right here, where you take the t out and put the 1 divided by 8 in the parentheses there. So we get 5/6 to the power 1/8, and then that is raised to the power t. So here we can do 5 divided by 6. Oh, we need this in parentheses to get the order of operations right. Make sure that all of the 5/6 is the base of the exponent. And oops, that's to the power 1/8, which gives you 0.9775. And so yeah, that is now the b is 0.9775. Now what is the r? We want to write this as Q equals 600 times 1 plus something. That something's going to be the r here. So oh, and that to the power t, forgot that. So the question is, what can you add to 1 to get you 0.9775? If you just subtract 1 from that, you'll get negative 0.0225. So that's what this is going to be, 1 plus negative 0.0225. So that's your R. You probably want to think of this as a percentage. Like what percent is it going down each month? So you move the decimal place over 2 spots to become negative 2.25%. And so that is the decay rate. If you want to call it a growth rate, that's okay. I'm just calling it a decay rate because of the fact that it's negative. It means it's going down. Okay. So that is a very tricky problem. Let's look at example 3. A quantity grows by 2% per year. By what percentage does it grow in 10 years? So we know the formula is going to be something like a times 1 plus r to the power t, but the r is going to be the percent it goes up by, and this time it says that that is 2% per year. So this is going to be 0.02. So that's going to be something that grows by 2% per year. Every time t goes up by 1, you multiply by 1.02. Okay, now what percentage does it grow in 10 years? Let's see. We can see what it will be in 10 years by plugging in t equals 10. And see how is that going to be different from whatever the starting value was, a. So with a calculator, we can do 1.02 to the power 10. It comes out to be 1.219. So after 10 years, there is going to be the initial amount, whatever a was, times 1.219. Now remember, thinking about the way we thought about this kind of thing in 6.2 is this is the same thing as a times 1 plus 0.219, which is a plus 0.219 times a. That 9 looks like an a. There we go. That's a 9. So this is whatever a was before plus 21.9% of a. There's something important to notice about this, which is that if it's growing by 2% per year, you might think that it's going to grow up by 20% in 10 years, because it's going to be 2% plus 2% plus 2%, 10 times should be 20%. Except for the weird thing that happens with exponential growth, is if it's growing by 2% in 1 year, then then you're starting with more for the next year. So the second year, it's going to grow up by 2% of a little bit more than there was before. And after that, it's going to grow up by 2% then a little bit more than there was before. So overall, how does it compare to the original amount? You end up getting an extra 1.9% out. Okay, so let's look at 2 more examples. This is a long video. We have a quantity that decreases by 15% per year. So by what percentage does it decrease each month? So I'll give you a warning here. It is not going to be 15% divided by 12, because if you're thinking 15% per year and there's 12 months in a year, it's a totally reasonable thing to think that it would be whatever 1/12 of 15% is, which would be 1.25%, 1.25%. But that's not actually quite how it works. So the way it does work is, what we're going to have to do is set up a formula for it. And to do that, let's think of the variable as a number of months. So if we say this is going to be Q equals A times B to the M over 12. Let's think of it this way. The B here, I can do it this way because I know what happens every time the number of months goes up by 12. So the B is going to be what is the yearly growth factor, which is what you get after 12 months. So that is going to be decreasing by 15%. Means that B could be 1 minus 15%. power m divided by 12. So every time m goes up by 12, every time 12 months goes by, 1 year, this is going to be 85% of what it was before. Okay, so yeah, I'm going to write that as a times 0.85 to the m over 12th. Now, what percentage does it decrease each month? That means every time m goes up by 1. Well, I'm going to try to write this as a to the 0.85 to the power 1/12, and then that to the power m, because again, you can multiply those exponents to get m over 12. And let's see what that is with a calculator. It gives you 0.9865. To the power m. So every month you're multiplying it by 0.9865. You'll have 98.65% of what you had before. So we want to think of this as a times 1 plus r to the power m, but we got to figure out that r. So that 0.9865 is 1 plus r, and if you subtract 1 from that, you'll get negative 0.01345. So that's what we have here, is 1 minus 0.01345. So what percent is it decreasing by? That, if you move the decimal place over 2 times, we'll see that that's going to be 1.345%. So yeah, it's not exactly 1.25%. It's kind of weird. So if it decreases by 1.35% in the first month, after that, it's going to be decreasing by 1.35% of a little bit less than before. And it ends up by decreasing by a total of 15% over the whole year. All right, one more example here. The population of this town in the year 2006 is 4,000 people, and it's growing at a rate of 1.57% per year. So let's write this in the form P equals A times B to the power T minus T0 to describe the population in year T. And let's notice that in 2006, the value of T is 2006, not 0, because we're talking about the year 2006. So what we want to do here is make it so that in 2006, when T is 2006, the exponent should be 0. So I think it helps to think of a little table here. So in the year 2006, we want to have P should be 4,000 people, where it starts at. And you can get that by doing 4,000 times something to the power 0. Let's see what that something is here. So if it's growing at a rate of 1.57%, then this should be getting multiplied by the B is 1 plus R is 1 plus 0.0157. 1 plus 1.57. So that's going to be 4,062.8. We can round it up to 4,063 people here. And if we multiply that again by another 1.0157 factor, we'll get 4,127 people. Okay, so let's see. The way we can get this is the 4,000 here. We basically want to do 4,000 times 1.0157 to the power 0. Here, this should be 4,000 times 1.0157 to the power 1. This one right here should be 4,000 times 1.0157 to the power 2. So what can we do with the 2006 to turn this into 0, and do 2007 to make this become 1, and take this 2008 and make that exponent become 2? This is the key here, is in 2008, if you want the exponent to be 2, you can get that by doing 2008 minus 2007. So here's the formula. It's going to be 4,000 times 1.0157 to the power t minus 2006. That right there is the formula that we need. If you plug in 2006 for t, the exponent will be 0. If you plug in 2007, the exponent will be 1. If you plug in 2008, the exponent will be 2. So that's the trick here. All right. This is a hard section. If you stuck through all these examples, thank you. And thank yourself, because you're going to need this stuff for doing the homework and the tests later on. Some of these questions are pretty weird and pretty hard. But you have a few to try to do on your own. I'll show you the answers to these in the next video.